Welcome, everybody. So, thanks for coming to another special colloquium. I'm glad to be able to introduce Xueda Wen, who's coming to talk today and visiting tomorrow as well. Xueda did his PhD at Illinois with Shinsei Ryu, and then did a postdoc with Xiaogang Wen at MIT. During his, I'm not sure if it was during your PhD or postdoc, but you were a KITP fellow at the Copley Institute for Theoretical Physics during your PhD.
Yes.
And prestigious place to go and visit as a theorist and hang out at the beach and do some physics and attend talks and hang out at the beach some more. And then since then, he moved to Harvard to work with Ashvin Vishwanath and in a sort of unique fellowship, postdoc fellowship, where he spends half his time at Harvard and half his time at Boulder with Mike Hermele. And so today he's going to tell us about conformal field theory and driven quantum many-body systems. So,
Yeah, thank you.
thanks, Xueda.
Yeah, thank you, Kaden, for the introduction. Yeah, it's my great pleasure to be here and introduce our recent stories on non-equilibrium physics. So my topic is about the driven quantum many-body system at the critical point. It's about heating, cooling, and beyond. So this is the formal title. So another title for this. Another title for this talk is Swing in Quantum Many-Body System. I believe most of us have played the swing in the playground, right? We know how to swing. But today I want to tell how to swing in a quantum many-body system. Okay. For many-body systems, we know that they are everywhere in our life, ranging from the neutron star to high temperature superconductor and to our own brain. Many body systems are everywhere and very fascinating. In addition, there are many rich features in many body physics. So Phil Anderson told us more is different. The meaning of this is that now if you give me a bottle of water, imagine that we know everything about the water molecule. It doesn't mean we can understand the phase diagram and the phase transition for this bottle of water, right? There are many rich things emerge as the particles become many and many. This is particularly true for this non-equilibrium system, because when there are non-equilibrium system, for the non-equilibrium situation, there can be new types of behaviors that are not existed at the equilibrium condition. Very nicely, such kind of non-equilibrium physics can be recently studied in our lab. For example, we can study very interesting non-equilibrium physics in ultra-cold atoms, in trapped ions, in superconducting qubit arrays. It's an exciting time to explore the new physics in non-equilibrium physics. Okay, so to give a concrete example, there are many new phenomena. How do I? Okay, good, thank you. There are many new phenomena in non-equilibrium physics. To give a concrete example, for example, the quantum thermalization. Imagine that we have a quantum system which is prepared in some pure state, which is described by a wave function. So at the beginning, each atom is decoupled from each other. There's no entanglement between the atoms. But at some time, if we turn on we change the Hamiltonian suddenly and let the wave function evolve in time. And then after a while, if you observe a subsystem of the atoms, you can find the subsystem looks like a thermal equilibrium with other regions. So this is called the quantum thermalization. The total system is a closed system, but the thermal equilibrium somehow emerged during this non-equilibrium physics. Yes.
So we've got some fluctuating sound according to the online folks here. Maybe as a quick fix, can we try moving the mic to your shirt instead
Oh.
of your suit jacket? That might fix it right now.
Yeah.
And if we're brave, we'll get the chat off of here. So
It's better now?
So I'm going to leave it. We'll see if it's better.
Okay.
You can ask the people online if it's better.
Yeah. Yeah, maybe I should keep my head fixed. I should do this. Yeah. Then it will be much better. Yeah. So, okay, so in this process, the dynamics is a unitary dynamics, but you can find the thermal equilibrium feature will emerge in this process. Why? This is because in this process, there is a formation of the quantum entanglement between atom and the other. Quantum entanglement played a very important role in this process. Okay, this is a very basic, interesting feature in non-equilibrium physics, and it was observed very recently in cold atom system. And in the most recent years, people continuously found new phenomena from many body scars to flock time crystals to merriment-induced phase transition. There are many interesting new phenomena. Okay, in all these phenomena, the quantum entanglement played a very important role. So the goal of our study, in particular in this talk, our goal is very simple. We want to understand and harness the quantum entanglement in this non-equilibrium physics and apply it in quantum information or any other area where the quantum entanglement will be useful. Also, we hope our physics or our approach can be universal. This means we hope the physics is not limited to a specific system. We hope it's universal. But at the same time, we have some challenge. So in this non-equilibrium physics, because the system is far from equilibrium, there are lots of excitations. So in this case, there are no efficient computational methods to simulate the non-equilibrium physics. There are some challenges. Our numerical tools are very limited. What should I do now? If I'm still interested in this non-equilibrium physics, but our tools are very limited. What should we do? Okay, then I ask myself, can we solve the non-equilibrium physics exactly by hand? If the numerical tools are limited, why not we just don't use it? Let's try if we can solve the dynamics exactly. Okay, so as I mentioned, we hope to find the universal physics. Then let's take a step back to the equilibrium physics. For example, when I look at the phase diagram for the bottled water, so there is a special point in this phase diagram, which is called the critical point. At this point, the physics is universal. What do I mean by this? Okay, let me be concrete. In this phase diagram, as we change the temperature and the pressure, along this line, there is a first order phase transition from liquid to gas. If you study the density difference between the liquid and the gas, you will find as we go to the critical point, this difference of density will vanish in this way. There is some critical exponent, beta. We can measure this behavior in experiment. On the other hand, in a totally different system, which is a magnet, if you look at the phase diagram, there is also a special point, which is a critical point here. As you increase the temperature, the magnet will lose its magnetization. And if you study how this magnetization vanishes as we approach this critical point, you will also find some scaling behavior. Very amazingly, these two totally different systems have the same critical exponent. They are the same. This is very amazing, right? This means some physics is independent of the concrete models. This is what we mean by universality class in the equilibrium physics. Why does this happen? This is because as we approach this critical point, the correlation length becomes larger and larger and goes to infinity, and the microscopic details are important. So at this critical point, something called scale invariance emerge. So what is the scale invariance? Let's watch a movie. So in this plot, this is a two-dimensional classical Ising model. So the black color is spin up, and the white color is spin down. In the first plot here, it is some random distribution of spin up and spin down. If we zoom in this plot by a factor 2, and then by another factor 2, and by another factor 2, you can find the configuration of the spin up and the spin down are different for different length scales. You can tell the difference among the 4 panels, right? Okay, now let's put this Ising model at the critical temperature, critical temperature Tc, and let it evolve in time. Okay, now what you see now is there are thermal fluctuations. The spin can flip because of thermal fluctuation. It can flip from up to down or from down to up. What's amazing is that at this critical temperature, after a while, if you look at the 4 panels, they look very similar. If you only watch one panel, you cannot tell the length scale. This means the statistic physics for the 4 different panels, they look the same. They are independent of your length scale. This is what we call the scale invariance. Because if you measure any 2-point correlation function, they are the same. They are independent of the length scale. Okay, this is the concrete meaning of the scale invariance. The physics is independent of the length scale. So to study the universal features in the non-equilibrium physics, we will drive the many-body system at such critical point. And in theory, people have developed some very good theory called the conformal field theory. This is not important here. The only important thing is that this theory captures the scale invariance at the critical point.
Sorry, I have a question. So, I mean, this whole picture, of course, which is true, beautiful, but this is equilibrium, right? So, in the parlance of conformal field theory, it means you don't have any relevant operators that form you away from the critical point.
Right.
But, I mean, conformal field theory is gapless.
Yeah.
So, if I'm going to come in, say, perform a global quench or something like this, I'm dumping a lot of energy into the system, why should I think that, you know, the infinite set of irrelevant operators, which are allowed to ignore equilibrium, aren't going to completely obliterate the system? I mean, in other words, for a real system to thermalize, it's not integrable.
Yeah.
It will have irrelevant operators, and how do I avoid those dominating dynamics?
Yeah, in the quantum quench.
Please repeat the question for the online folks.
Oh, I see. So you're asking why can we ignore the relevant operators in this non-equilibrium physics, right?
Yeah, because in a CFT, as you well know, is in principle, a 2D CFT is in some sense integrable.
Yes.
Right?
Yes.
So it's a very special type of field theory where we know everything. But if you drive the system far out of equilibrium, then what prevents irrelevant operators and collisions and non-integrable perturbations from just obliterating, from being able to make predictive statements about dynamics?
Yeah, so this is the point of this talk, because first we want to study these very universal features. So first we should fine-tune the system to the critical point. Sure. If you add a relevant operator, we will be away from this point. Then we are not. The dynamics will depend on the concrete lattice model, because if you are away from the critical point, some length scale will come in. Then the physics is not universal. So for our purpose, we will stay at the critical point and study what is universal. But that's a very good question. If we are away from the critical point, something else will happen, which we didn't answer in this talk.
No, but I'm still slightly confused because how can, I mean, the critical point itself is defined in equilibrium.
Yeah.
But if you're doing a quench, driving the system out of equilibrium, then what tells you that you can use the same principles of renormalization group to say, well, I can just ignore
Oh,
all
very
the-
good question. Yes, yes. Okay. Okay, very good. So when we do the driving, you can choose a different kind of driving. If you change your Hamiltonian to the off critical point, again, we cannot solve this case. Yeah, I will introduce to you what kind of driving we choose here. We will always drive the system, so the system stay at the critical point.
Does it mean it stays integrable?
Yeah, yes.
Okay.
Yeah, very good question. So we will stay at this critical point to find the universal physics. So now the question, yeah, this is a question. How do we drive the critical point? If you add relevant operators, maybe it will spoil the integrability. Yeah, the question is, how do we drive the critical point? Okay, we will learn from our daily life swing. So remember, how do we play the swing in the playground? So we simply deform our body in time. We deform our body in time and pump. Okay, there are two phases when we play swing. There's the one stable phase and one unstable phase. In this stable phase, we will simply oscillate around the bottom. And in the unstable phase, we can swing higher and higher. Okay, there are basically two phases, the stable and unstable phase when we play swing. It is easy to model this in the classical physics, but for our purpose, let's consider a quantum oscillator where you can find how to swing. Now we consider a driven quantum oscillator. This is a Hamiltonian with p squared and x squared. Everyone is familiar with a quantum oscillator. But the difference is now is to introduce a driving in this Hamiltonian. This omega here depends on time. So this is a very simple quantum mechanics. I think every one of us can solve this Hamiltonian, can solve this time evolution. The point I want to say is this. If you look at the operator x and p, you look at the operators and see how they evolve in time, you can find x and p are related to their original value by a 2x2 matrix. Very intuitively, this x and the momentum p will move in the fifth phase as we drive this harmonic oscillator. This 2x2 matrix is a 2x2 real matrix with determinant 1. This is a very simple SL2R matrix. You can find as we tune the parameters, as we tune the driving parameters in this Hamiltonian, there are only two cases. In one case, the xp will simply oscillate. So the energy doesn't grow. So this is the stable phase. And if you choose some other parameters, this x and p will move on this plane in this way. The energy will grow in time. This is the unstable phase. This is the two phases, what I mean by what we mentioned when we play the swing. Okay, if you solve this problem exactly, you can find as a function of the driving parameters, we can have a phase diagram, stable one and unstable one. Okay, this is a very simple quantum mechanics problem. You can solve it by hand within half an hour or 1 hour. It's very easy. Now the thing is how to play the swing in a quantum many-body system. Okay, let's go to the quantum many-body system. As we mentioned, we hope to study the quantum critical point, but here, for simplicity, we want to focus on the one-dimensional quantum critical system. So the well-known example of the 1D quantum critical system includes critical quantum Ising model and the Tomanagi-Latinder liquid. If you don't know what is Tomanagi-Latinder liquid, there's a colloquium here 2 weeks ago by Ruwan. he introduced the quantum simulation of this Comanaghi-Lattinder liquid in the lab. You can see some progress in Randy's group. Okay, there are some concrete quantum critical system in the lab. Okay, now what we do next? We want to mimic our deformation of body in pumping a swing. We need to deform our body in this quantum critical system. The way we deform the system is very simple. So at the very beginning, we consider a homogeneous quantum critical system. But now, as we deform the system, we simply deform the Hamiltonian density. So sure, there are other ways. You can add relevant operators. You can add some new terms. But for that case, that's more hard for us. Here, we simply want to deform the system by changing the Hamiltonian density in space. Okay, this is how we deform our body in pumping a swing. Next, we want to drive the system. We will drive the system in a very simple way. For example, you give me a wave function, the initial state. We will evolve the system by the Hamiltonian H1 for some time. Then we change the Hamiltonian to H0 here for another time interval. Then we repeat this process in time. Okay, we can drive the system in time in a very simple way, periodically. What's amazing is this. By choosing some very simple deformation of the Hamiltonian density, the algebra in this problem can be the same as that in a swing. The algebra can be the same. What do I mean? Let's give you a very concrete picture. When we drive this 1D system, what we can study is this operator evolution. This is the operator in the Heisenberg picture. When you drive the system, you can find this operator will move on the two-dimensional space manifold, which is a path integral, the space-time manifold, will move from one point to another point. So this moving is actually determined by this 2x2 matrix. Remember, in our quantum mechanics problem, the moving of x and p is determined by a 2x2 matrix, right? What's subtle is this. Here, this 2x2 matrix is not SL2R matrix. It is a SU1,1 matrix. What's interesting is this. The two groups, SU1,1 and the SL2R, they have the same structure. They are equivalent to each other. This means the algebra in this driven system is the same as the algebra in the swing problem. They are quite related. So more concretely, in the swing, yeah.
So am I supposed to interpret the z here as a complex number, x plus iy on the 2D space-time? Or?
Yeah. Z is x plus I tau. Tau is the imaginary time. Yeah, it is a space-time manifold. Yeah, this is different from the swing where the space is space x and p. Yeah, here is space and time. Yeah, this is different, but their evolution feature is the same. Okay, this is what happened in the swing. Now in this driven quantum critical system, again you can find there are two phases, stable and unstable. This stable one is similar to what happened in the swing. But for this unstable one, you can find the operator still evolve on a circle, but it doesn't oscillate all the way. It will flow from some fixed point to another fixed point. Then you will ask, why are the two algebra equivalent? Because you can find a one-to-one map between this one and this one. Okay, there's a one-to-one map. Their algebra structure is equivalent. Yeah.
So obviously this is some very special quench. Am I understanding that the only effect of time evolution is to move these operators around? They don't mix.
The operator.
So I mean, if I take a garden variety many-body quantum system, right, and I perform a quench, And in principle, one way to understand that is to solve the Heisenberg equations of motion for those operators. But the usual problem is that the operators will all mix with each other in some complicated fashion.
Very good. Yeah.
Right? So that picture, am I to understand that, say, Virasoro primary is not mixing with any other operator?
Right. Right. Exactly. This is very important because of the integrable property of the CFT. In general, this is not true, but here we are always place swing at the critical point. This can be true.
Because you're using the stress tensor somehow.
Yes. Yes. Exactly. Yeah.
Does that mean, sorry, could you decode this math? Does it mean that he only allows certain types of all operators?
I think it means he allows any operator, since the CFT gives you all possible operators, but the evolution is very special in that the operators only acquire, it's not a phase, but it's a SL2 motion in the plane. Right? So it's a very very special quench that doesn't blow the CFT away.
Yeah, later I will tell how to generalize this. Yeah, here we are simply using the SL2R structure. We can go to the Virasoro algebra. Please repeat the question. Yeah, I can repeat the question. So in general quantum many-body system, when we study the operator evolution, the operator will mix with some other operator. It will grow bigger and bigger. But here, the operator it doesn't mix with any other operator. This is because the critical point is integral. There are many conservation law. There are conservation law. There are integrable property. Yeah. So what does this mean? This means a simply driven one-dimensional quantum many-body system at the critical point is equivalent to place swing. So there must be two phases, stable and unstable. Yeah, let me give you a very concrete example. For any one-dimensional quantum critical system, we have a Hamiltonian H0. Now let's deform this Hamiltonian by a cosine function in space. Then we do this driving. Okay, this is the only input we need. We don't need to focus on any concrete lattice model. Okay, this is very general. Then if you study this time-dependent driving, the parameter that we can change is the time interval here. We drive with Hamiltonian H1 by T1, and then with Hamiltonian H0 by T0. Then you can plot a phase diagram similar to swing. As a function of time T0 and T1, you can find two different phases. One is unstable. The total system is absorbing energy. The other phase is the non-heating phase. It is stable. If you look at the energy growth, the energy simply oscillates. There's no energy growth. There are two different phases. Then we may wonder, what is the feature of this system in the heating phase? Okay, here are two plots. The left one is the field theory result. For the right one, it is a concrete lattice simulation. We find a lattice model, we do this driving, and we can simulate how the energy density evolves in time. Because as we mentioned, in the heating phase, the system will absorb energy. The energy will grow as a function of time. What we found is this. The energy density is accumulated at some special point. So the total energy is growing, but the energy density is inhomogeneous in space. Inhomogeneous space. Then, so what kind of thing determines the location of this energy density peak? As we introduced just now, there are operator evolutions. There are some very special points called fixed points. Such fixed points determine the location of your energy density. Okay, this is some very basic feature in the heating phase. We have found that the system absorbs energy, although the energy density is not homogeneously distributed. Okay, then as I mentioned, this driving is universal. It means the result is independent of concrete lattice model. Here, this is another work where people study the XXZ model, which is a spin model. Again, on the left is a field theory calculation. They observe the energy density peaks at some special point in space. And on the right is a lattice simulation of this XXZ model from this group. They found the field theory result captured the numerical result in this lattice model. So as we mentioned, our prediction should be universal. It should be independent of concrete models. Okay, this is energy evolution. We mentioned that quantum entanglement plays a very important role in this non-equilibrium dynamics. So quantum entanglement, to characterize this quantum entanglement, we use the so-called entanglement entropy. For example, entanglement entropy of this subsystem A captures how much this subsystem is entangled with the rest of the system. Given a wave function, we can obtain the reduced density matrix for this subsystem A by tracing over the degrees of freedom in the left part, in this B part. Then we can obtain the entanglement entropy for this subsystem. Very interestingly, in this heating phase of this driven system, we find, the entanglement entropy grows linearly in time. And in this non-heating phase, the entanglement entropy simply oscillates in time. Amazingly, at the phase transition along this line, we can observe the entanglement entropy grows at log t, and the coefficient is a very universal quantity, which is called central charge. For example, in the Tomonaga-Latinder liquid, here the coefficient C equals 1. And in the critical quantum Ising model, this central charge C equals 1/2. This is a very robust feature at the phase transition. Okay, a natural question is why does the entanglement entropy grow in time? How to understand the underlying physics? Okay, there are some interesting pictures underlying this entanglement growth. Okay, now what we plot here is this is a 1D system, one-dimensional system. We can find as we drive the system, at some point in the 1D system, some EPR pairs, which are entangled pairs. Some entangled pairs are generated at some special point. Then one member of this entangled pair is moved to one energy density peak here, and the other member is moved to the other energy density peak. What does this mean? This means that as we drive this quantum critical system, the EPR pairs are generated in time, and they are pumped to the nearby energy density peaks with a constant rate. And they are localized there. You generate EPR pair, one is here and the other is there. They are localized. Okay, then you may ask, so what kind of thing determine the location of the special point? Again, these special points are determined by the operator evolution as we introduced just now. Yeah.
So naively, if I think there's a finite spacing between these points, I should only be able to generate a finite number of EPR pairs, so the entanglement entropy would saturate. Are you taking like a limit where these points are further and further apart?
Very good question. So yeah, so this is in field theory, there's no lattice scale. So you have infinite degree freedom. The entanglement entropy in the previous slide, it can grow linearly all the way. But on a lattice system, there is a UV cutoff, which is a lattice constant. Finally, the entanglement entropy will saturate when the UV lattice constant comes in. So this doesn't mean we can generate entanglement entropy all the way. It will saturate. Yeah. very, very nice question. Okay, now we have seen this, we call this entanglement pump. We can generate these entanglement pairs, and this may be very useful as a source of entanglement pairs in quantum information. By driving the system, you can generate EPR pairs, and we use these EPR pairs in some other region, in some other areas. Okay, this is a periodical driving. Actually, we wonder if this is a robust feature if we consider other types of driving. For example, we consider the random driving. We also consider some quasi-periodical driving, which is called Fibonacci driving. It simply means as a function of time, when we choose the sequence of Hamiltonian. Either we can choose some randomly distributed Hamiltonian by deforming the critical point. We can also choose some quasi-periodical way. Here, the sequence is generated by some Fibonacci number. This is quasi-periodical driving. What's amazing is that we found, in both in periodical driving and random driving and this Fibonacci driving, this heating phase with this entanglement pump feature is always there. This is a very robust feature. It is independent of driving. You can always have this entanglement pump. Okay, this is some robust feature. Okay, then, okay, this entanglement pump is very robust. Then what is the application, right? You can apply it to generate some EPR pairs in quantum information. What other kinds of applications can we do? And another question is how to measure the entanglement evolution in experiments. You can do everything in theory, but if you cannot measure it in experiments, then it is not that useful, right? Okay, we will answer the following two questions below. Okay, so the application we want to introduce is this so-called cooling. So the key idea is this. This entanglement pump not only pumps entanglement entropy, but also pumps thermal entropy. So as we drive the system, some EPR pairs are generated in this region and redistributed to the energy density peak. But at the same time, if the system is initially in a thermal equilibrium with some bath, there are some thermal entropy in this system. What we found is that as we drive the system, this thermal entropy and also the entanglement, both of them are moved and accumulated to this energy density peak. In other words, this region is very cold. This region is very cold. But for this peak, for the location of these peaks, these regions are very hot. They are heating regions. So in short, the total thermal entropy of the total system doesn't change. We simply redistribute, we redistribute the thermal entropy by putting them at some very small region. Okay. This is a general picture. Okay, here I will show you a concrete result to show this cooling effect. So what I show here is the energy density in this cooling region. So before the driving, the energy density is here. The energy density, because there are thermal fluctuations, the energy density is high. But as we drive the system in time, the energy density will go down this way. And finally, it will become flat. So actually in this plot, there are two lines. There are red dashed line, which is a field theory calculation. There are also a green line, which is a lattice simulation. You can find that they agree very well. And So the energy density at the beginning and the ending, they have some concrete exact value. So here, the energy density is proportional to the temperature square. Beta here is the inverse temperature. As we drive the system, it is cooled down to this Casimir energy, which is the ground state energy of this quantum critical system. Okay, this is the energy density. You can already see some cooling here.
Xueda, before we move on, can I ask just clarifying questions? So, what determines the distance between the peaks?
Very good question. Remember that when we deform the system, we use some cosine function.
Yes.
There is some wavelength, L. This distance is exactly the same as the wavelength. So if you enlarge the wavelength, if the wavelength becomes larger and larger, the distance will also become larger and larger.
Okay, and then second, you're making a statement that if you were to integrate the, let's see, the energy density over the entire length L, it should be the same as before?
No, very good question. If we, the question is, so for this region, the energy density is becoming smaller and smaller. As we mentioned, the energy density, but at this region, it is hotter and hotter, which means the energy here grows in time. Actually, if we do an integral over the single unit here, a single wavelength here, we can find the total energy grows exponentially in time, which means the total system is always absorbing energy. Right. It's not conserved because you are driving the system. So the system is absorbing energy as a function of time.
Yeah. And maybe one more question. So when you compute the entanglement of the state, right, in the back of my mind, I thought we are still thinking about pure states, but clearly here you're talking about thermal equilibrium.
Very good. Yeah.
So can you still define, for a thermal equilibrium system, can you still define von Neumann entropy by dividing the system into two? I mean, surely you can, you get just two thermal density metrics, but what does this matrix look like here? Can you define a concept of local temperature as a function of x?
Oh, that's a very good question. Can I show you and I prepared a slide, but not here. I can show you. Okay. We can. The answer is we can. That's a very technical question, so I didn't put it in the main part of the talk. I will show you the result. One comment is this. In this case, the entanglement entropy is, there is not only entanglement entropy, but also thermal entropy in this system, because the total system is in a thermal ensemble. Now it's here. So now in this plot, we calculate the von Neumann entropy. Now we should not call it entanglement entropy because thermal entropy is also involved. If we calculate this von Neumann entropy in this cooling region, okay, here we have three different curves. This is the von Neumann entropy for different initial temperatures. We have different initial temperatures. But as we drive the system, we can find the von Neumann entropy decays to this ground state value, entanglement entropy. Here is the pure entanglement entropy. Here, there are both entanglement and thermal entropy. But the thing is this, no matter what is your initial temperature, finally, after the cooling, all of this, the different cases will go to the same ground state value. This means for arbitrary temperature, sure, it should not be super high. I mean, for arbitrary temperature here, we can cool down it to the ground state value. Okay, this is the thermal entropy. Okay, then the question, as we mentioned, you can study the quantum entanglement evolution, but the question is how to measure it in experiment in the quantum many-body system. Okay, basically now there are two ways of measuring the entanglement entropy in experiment. People can define something called Ryan entropy. the definition is as follows. You have some wave function. You can get the reduced density matrix for this subsystem. Then you can define your running entropy. Your n is some integer number. You can define n order running entropy. So currently in experiment, people can mainly measure the second order running entropy by choosing n equals 2. For example, in this experiment, to measure the second order running entropy, people need to consider two copy of the quantum many-body system and make them interfere with each other. This is a very complicated way, right? If you want to measure entanglement entropy, you need to make two copies. This is really not convenient. Another method is based on some more complicated way, which I don't know how it works. So they use some random measurement of the system, and they consider their statistical correlations. This is also verified in experiment, but they need a large number of random measurements, and they can only measure the second running entropy. Okay, then my question is there a very simple way, is there a simpler way in our driven one-dimensional quantum critical system to measure the quantum entanglement? Yeah, fortunately, we found that there is. Okay, so how simple is this method? So now, to measure the entanglement entropy in this subsystem A, we only need to know the two-point correlation function at the two ending points of this subsystem. For example, you want to measure the entanglement evolution in this region, you only need to calculate the two-point correlation function OX1, OX2 as a function of time. This is equal time, two-point correlation function. Then these two-point correlation functions are related to this running entropy evolution through this very simple formula. With this formula, you can not only measure the second running entropy, you can measure arbitrary nth order running entropy. We have a very simple formula. Actually, we tested this formula on lattice model, and it works very well. Okay, then the thing is, in experiments, how to measure this two-point correlation function. Yeah. Yesterday, I always believe this should be some simple thing in experiment. But after I talked to Randy this afternoon, I was told that measuring the two-point correlation function, like the density correlation function, like the spin correlation function, maybe not that easy. But yeah.
So is this only for the conformal field theory, or do you have lattice scale corrections here?
Yeah, this only works for at the critical point. If you are away from the critical point, we don't we haven't explored what will happen.
But even at the critical point, you have a UV cutoff, right? So isn't that going to change this formula?
Oh, very good. So the distance between x1 and x2 should be much larger than the lattice constant. If there are only 2 or 3 or 4 lattice constants between the two operators, then it may not work. We should make sure the distance is large compared to the UV length scale. Okay, yeah, maybe it's still not easy to measure the two-point correlation function in experiment, but once we can measure it, this will be a super simple way to measure the entanglement entropy evolution. Okay, that's it. Let's give a very short summary. So in this talk, I have introduced a very simple story on how to swing in quantum critical system. And also there's some application in quantum cooling. And we can also have some simple way of measuring the entanglement entropy evolution. Okay, there are many future directions, but yeah, one thing that the first direction is what Matthew asked me just now. Our driving here is some special driving. What about some generalized driving by adding the relevant operators? Yeah, this is an open question to me now. And also here, we didn't introduce the dissipation, the effect of dissipation. Imagine that if we introduce a dissipation, there will be a competition between driving and the dissipation. There is a competition. Maybe there will be something new here. And we can also generalize this driven system to higher dimensional critical system. And we also need to go to the off-critical system. I mean, there are many questions. So, okay, and at the end, I want to thank my collaborators. I learned a lot by working with my collaborators. And yeah, with this, I want to thank you for your attention. Thank you very much.
Thank you for the beautiful talk, Xueda. Questions?
Actually, can I answer Andrew's question just now? Andrew asked me the question. Yeah, this is the first slide I prepared here. Andrew asked me for the cooling region, if you can define a local temperature. You see, I write the local temperature here. Yes, we can. So for this reduced density matrix, it is related to this to the entanglement Hamiltonian in this way. This entanglement Hamiltonian is an integral of the local Hamiltonian with some local temperature here. So before the driving, this local temperature, if in the bulk, this local temperature is the same as the initial temperature. But as we drive the system, this local temperature will go up. This is the inverse temperature. So the effective temperature is becoming lower and lower. So finally, we will arrive at this ground state. This dashed line is the ground state local temperature. This shows the cooling effect in the level of this reduced density matrix. Yeah, we can study this. Okay.
So why is the yellow curve asymmetric?
Oh, very good. Here, in this entanglement Hamiltonian, there's a chiral part and anti-chiral part. Here, this plot is only for this chiral part. If you include both the chiral local temperature and the anti-chiral local temperature, it will become symmetric. Yeah.
Yeah. So, what is the relevant temperature regime here? What sets the scale for the relevant temperature? And can you put it into a unit that is a lab unit?
Yeah. Very good question. So in the lab, when we study a quantum system, there is some energy band structure, right? There is bandwidth. So to realize, to study this effect, we require the temperature should not be that high to excite the quasi-particle to the top of the band. So we hope the temperature scale should be KBT, should be much smaller than the bandwidth of the system.
So you're talking about the bandwidth in the radial direction, because the axial direction could either be continuous or is it a Hubbard model in the axial direction as well?
Oh, what I mean by energy band is for the system, you can calculate the lowest energy and the highest energy, the difference between these systems.
So you're not in quasi 1D, you're in 1D.
1D, yeah, 1D. So it's not a two-dimensional.
So the relevant temperature scale is h bar omega z. Some kind of, is there an axial energy scale that's relevant here?
Yeah. You should compare KBT and this.
But it would be like in the Fermi gases, it would be the size of the linear dispersion, right?
Yeah, exactly. So for that part, it is described by the conformal field theory. If you go to the nonlinear part, this field theory will fail.
So actually, that's a good question. Okay. not solvable anymore. Can you say something about what happens?
It's no longer so. I mean, numerically, we can always always check. But in the field theory, I don't know. Currently, I don't know how to introduce this effect and solve it.
I mean, technically, we're probably using kind of informal perturbation theory, but
Yeah.
I guess the question is, I mean, presumably, in general, for this type of setup, where you're taking a CFT and you're driving it in a very, very special way, you're going to have all sorts of things that can contaminate this, right? Like, probably a pretty gentle one with something like band curvature, but you also have real collisions between the particles due to unclop scattering and other things that are not integrable perturbations. So, I mean, do you have some idea of like what's going to be the most limiting factor? I mean, it's going to be system dependent.
Yeah. So first for the driving, let me see step by step. In the main part of this talk, we consider some very simple deformation of the Hamiltonian, like cosine. If you go to some very arbitrary deformation of the Hamiltonian, we found first for this kind of deformation, we found the conclusion, the basic feature is still there. Sorry, I didn't add a reference. There are two papers here working on this by generalizing this simple deformation to some very general deformation. What we found is there are still two phases, heating and heating, and the entanglement pumping is still there in heating phase.
How is the calculation? I mean, we should talk about the subline. How is the calculation done? I mean, can you still just somehow use this SL2 algebra, or you have to, or this is DNOG?
Very good. In this case, the algebra is no longer SL2, it is a Virasoro algebra. It's Virasoro algebra. But in the field theory level, even in this case, we can still calculate the evolution of an operator, but only it's still a field theory calculation, but we have to use numerics to do to show the operator evolution. Once we know the operator evolution, we can calculate the phase diagram and the entanglement evolution. Yeah, we need to combine with numerics in this case.
Xueda, so one question is about maybe what Randy asked, can you put it in real units? So I noticed that this effective temperature that you describe, the upper limit on beta depends on L, little L being, the periodicity of your drive in real space.
Right.
So if you want the temperature to be lower and lower, you have to increase the spatial variability of your operators, right? So in practice, one could presumably put some, the relevant scale, let's say in Randy's experiment is, 50 lattice spacing along the chain or something like that, right? So there should be a fundamental limit if you're giving a chain with finite lengths instead of an infinite Lagrange liquid. There should be some edge effects where what you described here would be limited. Did you try,
the edge
colleagues
effect.
try to do DMRG on finite cylinders and see what happens?
First, okay. First, in this field theory calculation, we consider an infinite long system. This is what we can do. We can also do a finite system with a boundary, a conformal boundary condition.
Yes.
In the field theory level, the conclusion doesn't change much. I mean, even if you impose a boundary. But I believe in the lattice model, if you consider a very small system, right? For example, in the calculation here, in this lattice calculation here, we choose the site to be like 200 site. They already agree very well. But if you make the lattice length smaller and smaller to like 30 or 20, sure, they will not agree that well. We should choose the lattice length as longer as possible.
And could I ask a more general question about motivation? So you started from describing the example of a critical systems.
Yeah.
And of course, the legacy and why people were interested in them is because of the universality classifications, but also an emergent phenomena that happen at the critical point, right? Like you mentioned, self-similarity at different scales. Now, as Matt alluded to, it could be that there's a lot of interesting phenomena in driven system that don't happen in exactly solvable perturbation.
Right.
So so, you know, I guess it's a question of motivation. I mean, do you believe in your heart that the kind of physics that you're getting here with CFT is all that's interesting and everything else is boring, or should just do DMRG on it?
Yeah. Very good question. You know, our motivation is very simple. First, we can say, now for the exactly solvable one, how much we can explore, right? I believe that some interesting physics cannot be solved by analytical method. I totally agree. Yeah, my motivation is even in this exactly solvable limit, there are some interesting physics which we didn't know before. This is what I want to share in this talk. Yeah, in general, I totally agree with you. We need to study some more general systems. You need, finally, you have to use numerics. Yeah, I totally agree. Yeah. But
One last question here.
Hi. When you are saying your kind of theory is universal, you're mentioning like it's something you can distinguish these different universality classes in your like your conformal field theory type. Is that similar for you to have the exactly the same conformal field theory type of universality characterization in these non-equilibrium systems?
very good, very good. This question is about the universality class. Okay, what we found is this. We found it's not only universal, it is super universal. So what I mean is this. I introduced this phase transition for the entanglement entropy evolution. So for different universality class, usually this central charge can be different. We have, so the feature here depend on different universality class. But if you study the critical exponent, what I mean by critical exponent is this. There's a linear growth of entanglement entropy in the heating phase. As we approach the phase transition, this linear growth will vanish in this way. And this component, we call it a critical exponent at the phase transition, is super universal, means for different universality class, this component is the same. This is why I call it super universal. Similarly, for this non-heating phase, the entanglement entropy oscillates in time. If you look at the oscillating period, this oscillating period will divert as we approach this phase transition. It diverges in this way. The critical exponent here is also independent of which universality class you are in. This is also what we mean by super universal. So indeed, there are some not only universal but super universal feature in this system, in this driven system.
Great. So I think that's a good place to stop. If you have further questions, feel free to come up and continue the discussion. But with that, let's thank Xueda again.
Thank you. Thank you. Yeah, thank you very much.